let's pick up where we got to. So for those that haven't watched the video from yesterday, where I get that bit right, by the way, we introduced this formula here. There is a proof for this formula that we haven't done yet. And we are going to do it, but we're going to do it when we're all a bit older and wiser. And this formula allows you to work out the sum of the first few terms, n is how many terms, of a geometric series. So series is a sequence where you're just adding it together. And all you need to know is the first term, the common ratio, which was the multiplier, if you remember, and the number of terms. So in this question here, which we did yesterday, so it's in the video, I forget actually, I think I might have stopped the video, but yeah, we would say, right, the sum of the first 3 terms in this question, sorry, the sum of the first 8 terms is what they're asking for, is just, first term is 5, so it's 5 times 1 minus 2/3 to the power of n over 1 minus 2/3. And you can just whack that into your calculator. N is 8, and you get that answer there. Really, it's about plugging numbers into a formula. The difficulty with the logs comes when you don't know n, but in this case, we knew n. And so that was all very well, and I'm rushing through that because we did that yesterday. So, and if you want to, that's on page 72, so you can go back and have a look at that result. If I apply the same principle to this question, the first term is 8. I don't know r, but n is 3. So I can write a formula for the sum of the first 3 terms. It is 8 times 1 minus r to the power of 3 over 1 minus r. And we're told that that is equal to 30.5. The problem with that is that when I multiply both sides by 1 minus r to kill the fraction, that gives me a cubic equation. You've got an r cubed term there. You haven't actually got an r squared term at all. You've got an r term and you've got some numbers. And we know we can cheat and solve that on our calculator, but nobody knows we can do that. We aren't actually able to do that. So that's not going to work. So that approach breaks when you get a question like question 4. And so this is where we got to at the end of yesterday's lesson. I said, right, what I want to do is show you how we can approach this question. And it's a really neat trick. And it's really very, very basic. So instead of using the formula for the sum, and a reminder that that is on the formula sheet, so that's not something you need to remember, but instead of using that, what we do is this. We say, okay, this sequence, we're only dealing with 3 terms. If the first term is 8, give me some algebra, Callum, for the second term. How? Let's 8 times r. And Arthur, give me some algebra for the third term.
8 times r squared.
8r squared. And we're told that the sum of those 3 terms is 30.5. That is a quadratic. That's a quadratic. So go on, have a go. Just line it up and use your calculator to solve it. Bob will be around. And so we get the answer, quite quickly and easily. And there's the reassuring use of the plural in the question. So they're not then asking us to decide which of those two is valid. They're both valid. We're not told anything. If they told us that every term was positive, then it would have to be 5 over 4, because with a negative value of r, this sequence oscillates between positive and negative. So how do you know whether it's a question where the formula will work or one where the formula doesn't work? Well, there's no easy answer to that. I would try the formula first. That's what I did with question 4, and it didn't work. So that's where I started hunting for an alternative approach. So for those that weren't here, we ought to perhaps practice one where we do use the formula. So question 8 is one where the formula does work, and you actually use the formula twice to generate some simultaneous equations. So we know nothing about the sequence, so we're going to have to use A and R, but we do know that when n is 2, the sum is 4.48, so we can use the sum formula to get an equation there. And we know when n is 4, the sum is 5.1968. So we can get 2 formulas, one for the sum of the first 2 terms and one for the sum of the first 4 terms. And it's funny, when I practiced this one, I thought, this is like question 4. So I wrote out the first 4 terms and tried to add them together. It didn't work. So this is one where the formula definitely works. Let me write the formula up again. So we're going to do the sum of the first 2 terms and the sum of the first 4 terms. And then we need in some way to combine those 2 equations to get a solution. We're after 2 possible values of r. So I have written the formula making n equal to 2, and we're told that that is 4.48, and I just then multiply by 1 minus r to give me this. And I've done the same for the sum of the first 4 terms, giving me this. And this next step is just such a beautiful step. I don't know if anyone spotted it. This here. So what was it? It's not 1. It's very close. It's not 1 minus r squared, but it is something squared take away something else squared. It's a difference of 2 squares. It's this. So that factorizes like that. So it's like, the ones like that, which become x plus 3, x minus 3. Well, r to the power of 4 is r squared squared. So you get this, and it's just... And then what can I do? Well, look, this thing here features there. So I can replace that with that. And that means all of a sudden I've got no a in my equation. I'm now down to an equation with just 1 missing value. So I'm now going to look, having factorised that, this thing here is the same as that. So I'm going to replace it with 4. Now we have to do a little bit of a cheat at this point and assume r isn't 1 for the next step to work. Let me give you a minute just to have a think about how you can do that next step. There's some cancelling, and then there's another difference of 2 squares in there. Can you spot it? Okay, as long as we agree R isn't 1, if we go on and find out that R is 1, we're in trouble, but I can divide both sides by 1 minus R. Yes, Sean?
Aren't you safe to assume that R isn't 1 because of...
You're absolutely right, aren't you? Because this isn't double that. Yes, good question, good point. Yeah, if R was 1, you'd basically have the same term just repeating again and again. So the sum of the first 4 terms would be the sum of the first, double the sum of the first 2 terms. Thank you. So let me rewrite what we've got. And actually, I was going to say this is another difference to 2 squares, but we don't need to do that, do we? Because it's just a quadratic now. It's just a quadratic, and it's even better than that. It's a quadratic where you haven't got any R terms, so you can use your calculator, but you can also just write it as R squared equals and square root it. Yes.
I don't know if it's me being silly, but is it the 1 plus R squared? Because the 1 minus R squared...
Thank you. Thank you. Thank you very much. It's never you being stupid, we know that by now. See, I haven't got any biscuits, but there we go. So we factorised that into that. We replaced that with this from the first equation because we were told that that equals that from the first equation. Moving to the top, we then divided by 1 minus R, and then it was just a quadratic. And of course you could have just lined it up and solved it using a calculator, but R is plus 0.4 and minus 0.4. And again, reassuring use of plural, we're dealing with 2 possible values. Okay, so let's now consider, what happens to these geometric sequences for different values of R. And I pointed out yesterday that what we're actually dealing with here is exponential growth, aren't we? So if we are dealing with a value of R that's greater than 1, we'll have our starting value here, and the sequence goes like that. If R is between 0 and 1, then there's our starting value. The sequence goes like that. But it's never going to reach 0, is it? It's never going to reach 0. If R is less than minus 1, so you're multiplying by a negative number smaller than minus 1, I'm assuming that it starts on a positive value, that you get this sort of, it's going to be, going like that, isn't it? It's oscillating between positive and negative, and each oscillation takes you further into positive and further into negative. And if R is between, got to be careful here, minus 1 and 0, so it's negative, but it's a tiny negative number, less than minus 1, then you're going to get that sort of scenario, aren't you, where it's oscillating between positive and negative, and each time you're multiplying by a number between 0 and minus 1, it's getting smaller. So we're dealing with 4 scenarios for how the values in these geometric sequences vary. Exponential growth and decay, fairly standard, but then this sort of negative issue as well, with the terms becoming increasingly bigger, oscillate between positive and negative, and increasingly smaller, oscillate between positive and negative. So my next question is then, that's what happens to the terms in a sequence. What happens to the sum of those sequences? Now, hopefully we understand that here the sum is going to get really, 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 really big. And here the sum is going to get really, 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 really big. If it starts positive, oh, hang on a minute, is that going to get really, really... Well, I guess it depends at which point you stop, doesn't it? Depends at which point you stop. But yeah, this sum is going to get either bigger positive or bigger negative, depending on where you stop. So I'm more interested in what happens to the sum in these 2 scenarios. Okay, so this is my question. What happens to the sum when r is between -1 and 1? When it's a sequence that's getting smaller, albeit one where it's positive and negative or just a normal one. And we've got another way of writing that. We can write it like that. The modulus of r means the absolute value, not positive or negative. We've used that notation elsewhere, haven't we, for the length of a vector? But one of the things we do in this year.
Oh yeah.
So yeah, but not. I think the pattern is still the same regardless.
Are you happy with that? All right, no mistake?
Yes.
Can you sharpen my pencils?
I certainly can. So what I'm going to do is I'm going to fire up Excel, okay? Because I don't want us to have to do all manner of calculations ourselves. So here we go. So I'm going to use Excel to generate a couple of sequences for me. Let's zoom in a bit. So let's have a sequence where the first term is 100. And each time we are multiplying by 1/3. Okay? So this is a sequence where r is between 0 and 1. So okay, so it's generating terms in that sequence. That's how it writes standard form in Excel. So this is 1.18 times 10 to the minus 10. That's a tiddly number before you get some. So what I'm now going to do in my second column is work out the sum. So the sum after one term is 100, and then this sum is equal to the number above plus the new number in the sequence. So let's now, and what you find is this. So obviously for a while the sequence is getting a little bit smaller, but it's still, you know, a decent size. So every successive term is making the sum a little bit bigger. But eventually you get to the point where the numbers are getting so small. So this is 6.27 times 10 to the minus 5. So that's 0.00000627. But it is making no discernible difference to the sum. So what you get in half of this scenario is a situation where the sum starts getting bigger, but eventually sort of tops out. And that's because the terms, because r is a small number, the terms are getting smaller and smaller and smaller, and they're so small that they're not making a discernible difference to the sequence. What about if r is a small negative number? So let's go up here and let's change my formula to minus a half, say. Is it going to let me type it like that? Well, right, okay, so let's generate that sequence. I think I went a bit over the top, didn't I? And let's look at what happens to the sum. Same effect. The sum is jumping around because it's, it gets bigger, then it gets smaller, gets bigger, then it gets smaller. But eventually, it zeroes in on a single value, which in this case looks to be 66 2/3. So when we have this situation, r is a minus a very, very small number, we have the concept of what we call the sum to infinity, which is the value the sum approaches as n gets large. This only works in this scenario, where you've got a value of r that's very small, either positive or negative. Let's have a look at the sum, the normal sum formula. Now, so this is the normal formula for the sum of any geometric series. If r is small, and n gets closer and closer to infinity, although actually, according to Excel, we were hitting there, after about 50 terms, so we're not talking very close to infinity. Can anyone tell me anything about any terms in that formula? R is a little number, and n is a big number. Well, there's only one term in this sequence which has n in it. So what's going to happen to r to the power of n, Sean, as if r is small and n gets really, really big?
It'll get smaller.
Yeah, so if you think about a half squared is a quarter. A half cubed is an eighth. A half to the power of 4 is 16. And so on, 1/16, sorry, etc., etc., etc. As if r is small and n tends to infinity, that formula becomes the sum to infinity, which is a over 1 minus r, because this becomes 0, so 1 minus 0 is just 1, and a times 1 is 1. Now actually, that proof you don't need to worry about, because the sum to infinity formula is on the formula sheet. So if that last bit, if all this malarkey has left you covered, it doesn't matter, because as well as this sum is on the formula sheet. So, sorry, Sean, I haven't sharpened your pencil yet. Let's. We call series like this convergent, okay? So if this is true, we say that it's convergent. And so the test for convergence is showing that r is a value between -1 and +1. So have a go at this question. Firstly, work out what r is and show that it's small, and then use our new formula to work out the sum to infinity. Do you know what? There's a tutor group in here that when I'm not here, I have a suspicion that other people might be touching my pencil.
You're going to have to take it wherever you go, so.
Well, yeah.
Protect it.
I may have to take all of this with me. So you've got to firstly work out R. To show this is a convergent series, to show we can use the sum to infinity, we've got to show R is small. So we've got to use the fact that we know the 4th and the 7th term. I'm going to draw a picture. You may choose to do it using algebra. So in order to answer A, all you've got to do is to say, right, R is this, which is between -1 and 1, therefore it's convergent. That's all. Then you can use the formula. You don't use this formula if you're being asked for the sum to infinity. You use this formula. You could still be asked for the sum of the first 10 terms, in which case you'd use this formula. But having shown that R is a small number, we've been asked to find the sum to infinity, then it's A over 1 minus R. Yes.
Is this how you prove this? So you have to take the limit of separated from infinity and show that that connects to 0. Thank you so much.
So I've shown the series is convergent. So that means that I can use this formula here. I don't yet know the first term, so I need to do 1.08 divided by r cubed. So I divided by 0.6 cubed. So that's 5. My first term is 5. So it's 5 divided by 1 minus 0.6.
Yeah.
12.5. 12.5. Bingo bango. Right, we will leave it there. We'll leave it there.